as we look through today. A second method is a reverse model of hypertrophy, was to take away loading and watch the muscle shrink. Does anyone have a cast on one of their limbs ever? You know how horrified you are when they take the cast off? Like, where did my leg go? Right? And then it's kind of amazing how quickly it comes back. Well, that's a reverse model of growth. So here's 2 weeks of immobilizing a rat's forelimb or hind limb, and their tibialis anterior shrinks. The cells inside shrink because they're not bearing any weight. Oh, by the way, just to reinforce, if you do fiber counts, you don't lose cells, you lose fibrils inside each cell. Same number of cells are present, they're just small. Okay? Now, when we do this in actual rodents, the unloading model is kind of cool, the way it works. You take a little cuff of, like a croquis on a sunglasses, and instead of putting the earpiece of the glasses in, you put the rodent's tail in it, and it holds it like a Chinese finger trap. Then you suspend the tail, and you've got a dual pulleyed system, so the rat can run around its cage as much as it wants on its forelimbs, but the hind limbs have been relieved of loading. So you get really nice, and so we ought to see atrophy, and we're looking at 2 muscles. We're looking, the purple is tibialis anterior, which is really a placement muscle. It lifts the foot like that. And we're looking at gastrocnemius. Can anyone tell me why the gastrocnemius in blue, oops, I said it wrong. Yes, the gastrocnemius in blue is losing more mass? Ignore these labels up here, I don't know what they mean. It's clearly labeled down here. Why would the gastroc lose more mass than the tibialis anterior? Yeah, what is the gastroc normally doing? Supporting all of body weight, whereas the tibialis anterior is simply lowering the paw. And so the rate of unloading, the amount of load that's been taken away is much different. The anti-gravity muscle loses the most mass because you've changed its workload the most. Does that make sense? Now, a cool thing about the hind limb suspension model is you don't leave them this way. Eventually, you're going to drop them back onto their legs, right? And then you have a reloading study. So you actually do get to a true hypertrophy model, but it's very much like what happens to us after a cast is removed. We go back to normal activity, and the muscle rapidly regrows. And so here's that same study showing the post period. Here's hind limb suspension. 3 weeks later, you take off the tail trap, and notice they rapidly regrow. And once again, you'll see the muscle that experienced the most unloading and then has the heaviest reloading recovers or grows most, which is, you'll see a lot of evidence that load is still tremendously important. Morgan said something about that. All right, well, that's very nice. So for the rest of this lecture, what I'm going to do is go through, I really like this because we don't often have the time in your busy, busy curriculum. I'm so sorry about scientific knowledge doubling every 30 years. I didn't do it. But we seldom have time to slow down and actually show you science process. Like, how do we know this? And so what I'm going to do is take those 4 or 5 mechanisms that we know work to grow bigger mammals, and we're going to take adult animals and see if we can either stimulate those mechanisms further or remove them and watch what happens. And you'll be shocked that in most cases, you don't need IGF-1 to grow bigger muscle as an adult. You don't need high levels of testosterone as an adult to grow bigger. You'd be amazed how much the evidence points to that mammals undergo a series of controlled growth steps, and then most of it turns off except for this one mechanism that we're going to see by the end of the lecture. So I showed you this slide in advance. Some of the ideas are that in order to enhance protein synthesis, perhaps you have to add more myonuclei into the cell, as though you didn't have enough DNA to actually get high levels of transcription and translation. These are very popular, I'm saying, especially among, can anyone tell me why high school coaches are particularly big on the testosterone estrogen hypothesis? Who are they watching all day long? If they're watching 13 to 18-year-old men, boys and girls turning into men and women. And so they become very convinced, but it's a observer bias. You'll see. And then there's this idea, many of you may not know this, but this is going to turn out to be the only mechanism that seems to survive into adulthood and which seems to manage what I call adult adaptive hypertrophy. The icing on the muscular cake to fit you into the particular environment and use patterns that your culture or environment makes you do. So that's a foreshadowing of where we're headed. So let's go through some of these mechanisms, which I call factors not critical to adaptive hypertrophy in adult resistance training. So the idea of satellite cell recruitment would be that in a normal muscle fiber, this myonucleus, it's responsible for a certain area of what we call the myonuclear domain. It's responsible for a certain area of cytosol in providing transcripts, mRNA, of critical factors. So in the satellite cell recruitment model, people say, well, let's say that there's a lot of these nuclei. Each one is straining. It's right at the edge of its abilities. It's already maxed out. And so if you grow a bigger muscle, there's no way that that nucleus can cover more cytosol. You've got to recruit a new satellite cell. This is testable. We're going to test it next. I found this in one of the articles. This is scanning EM, where they had skinned back the endomysium. And you'll notice you can see how the actual myonuclei look like pigs in a blanket, so to speak. There's a smooth contour because they're beneath the actual sarcolemma. And then do you see how this one has almost like a shadow, a stuck-on property? That's a satellite cell. So we've actually found a satellite cell, and we have a picture of one. I like that. Okay. We're going to skip this and talk about it later, but the concept we'll come back to this, but the idea that you're limited in the amount of DNA you have and that transcription is critical, that's one of the ideas that causes the satellite cell hypothesis, which you can find in textbooks. You can find textbooks for a class like this that claim this is the answer, despite an abundance of evidence that it's not true. So we have three models, three hypotheses of way to think about this. Here's your basic muscle cell with 4 myonuclei, and each one of them is providing, I call it nuclear support, providing transcripts and other nuclear factors to 1/4 of this cell in cross-section. Okay? So hypothesis 1 is saying you can have no growth unless you recruit satellite cells. So watch. This is your first, and then it goes through growth. So basically the volume of this cell has now doubled. And the way the drawing is going is that in order to do that, you must then undergo satellite cell recruitment to double the myonuclei. See that? And then if it grows again to 3 times the original size, you must add 3 myonuclei. So this is saying no growth without satellite cell addition. I'll be able to disprove that pretty nicely in a moment. The second hypothesis is the other extreme, that there is no growth. Oh, sorry, I said it wrong. All growth takes place independent of satellite cell recruitment. Where, see how the cell here has tripled in size, and each time the nucleus is able to simply up its game and secrete more transcripts for the use in cytosol. You see that? Okay. This one, at least theoretically, will ultimately become, this can't be true once you've increased the cell to 3 millimeters wide. You're at some point going to run out of diffusional distance. There's got to be a limit on this. Well, as it turns out, the evidence when you look at human studies, animal studies, this is the muddle in the middle. Hypothesis 3 says that an untrained muscle the myonucleus is not strained to supply that cytosol, and that muscle can undergo significant growth before you actually start to run out of myonuclear support. And between Dr. Bodine and I, since we were both interested in this, and I approached it from the human model and she approached it from the rodent models, we each came up with our own idea of where is this level? Where do you start to really need satellite cell recruitment? You have to basically double the size of a muscle from its original, and very, very few of us have done that. Okay, so just realize that there is a point at which satellite cell recruitment becomes important, but most people are never going to reach that point. Right? So this is the one that humans, and this seems to work in mammals, that there's a certain reserve that each mononucleus has. If the muscle grows more than 100% in size, doubles its size, then you start to see evidence. So here to show you that I'm basing this on a lot of information, here are 9 resistance training studies, including both men and women. Notice, as I said before, most resistance training studies done scientifically are shorter than 4 months long. It has to do with the length of a quarter or a semester. The muscle, they got nice levels of growth. The minimal level, oh, here they didn't grow too much. I bet they did thighs. It's hard to get quadriceps to hypertrophy. You really got to work at it. But you have nice levels of growth. And then this column is showing you the myonuclear content. So was there evidence for satellite cell recruitment? And notice that all of them have no change or non-significant changes. Except for, all of them have no change with only 2 studies. This is quite small, and that is so strange that it makes you wonder what they were doing. By the way, if anyone in your study is using steroids, you automatically get satellite cell introduction, and it's not because it's a basic effect of the exercise, it's a basic effect of the drug. So one has to be cautious when you start to see those things. All you would need in this study is to have 20% of your subjects who are male using steroids, and you'll get that result. So here's a more direct, so that would be sort of like an observational study. We'll put humans through regular training programs and see if their myonuclei increase, and generally they don't. Here's an actual intervention study. Tamoxifen is an estrogen-blocking chemotherapeutic agent that some of you may be aware of if your moms have had a brush with breast cancer. But one of the other effects of tamoxifen is it blocks satellite cell recruitment. And so let's go through this because it's a little bit complex graph. Let's first look at satellite cell recruitment. So when satellite cells begin to differentiate in the myonuclei, they begin to express PAX7, which is a specific gene that says, it's like declaring your major. They declare their major to be a myonucleus. And so this would reflect satellite cell elaboration or reproduction. Notice tamoxifen blocks it down to about 1/5, 20% of normal satellite cell recruitment. And yet, when you look at the total muscle weight, when you do that plantaris hypertrophy model, compensatory overload, they grow identical whether you give them tamoxifen or inject them with saline. So you don't need satellite cells. And remember, the levels of growth that you're seeing in compensatory hypertrophy are what you would get out of maybe 3 years of human intense training. To double a muscle takes a lot of time. And so you're seeing large-scale changes in the muscle weight, basically almost a doubling, with no satellite cell recruitment. You see how Bodine and I reached those conclusions by looking at the... Good. So satellite cell recruitment, and by the way, I'm not trying to tell you it doesn't happen. It happens oh look, I have a thigh. It happens tremendously when you're born and your thigh is this big, and over time your thigh keeps going, your bone keeps growing. You do add satellite cells because your muscle isn't simply doubling in size. From babyhood to 20 years old, most of you have increased the volume of your muscles by 20-fold. So satellite cell recruitment is tremendously important growth, and it's tremendously important in adults when we damage muscle. Mary?
I have a question about tamoxifen. Yeah. If it's also an estrogen
Blocker.
Does that mean that it's an androgen receptor blocker as well?
To my knowledge, it's pretty specific to estrogen. These animals are mixed group. They're both males and females. There's a homogeneous response. Good question. But that's really nice because what Mary's question is leading to is, so what about hormone balance? Everyone will tell you poor old, God, what is his name? One of the scientists who back in the 90s just committed to this hormone thing, started measuring, cortisol, testosterone to cortisol ratio, right? Testosterone makes muscle, cortisol breaks it down. 10, 20, 50 studies on this. Sorry, but never an effect that was worth looking at. So sorry. So, I mentioned before that testosterone and estrogen are both anabolic hormones. Estrogen does add tissue. It tends to add feminine placement of fat. Girls turn into women. And it adds muscle. Most people don't appreciate that estrogen is an anabolic hormone. The muscle is added in the lower limb particularly. I'll show you graphs on this. The thighs and calves of women become much stronger as they move through their adolescent growth spurt. Men have a leftover gorilla phenomenon. It truly is. It's a primate sexual dimorphism, and so there's more response to testosterone in the upper body, so men grow in their limb girdles more. Upper body. Anyway, so as long as this testosterone is delta-ing, or estrogen, it is a growth signal. Once it stabilizes, and I mentioned this last time, this study has been done at least twice, where one was in young men, one was in old men. It does not matter if you're an 800 or a 350 and you go through a training program as an adult, you grow exactly the same. So testosterone stable does not appear to be a growth signal. It does maintain your sexual function, but it's not a muscle growth signal. With that, now this will give you an explanation too of when you use anabolic steroids, what are you doing? You do not forget about YAMS, forget about prohormone. I once saw an ad that said, doubles your testosterone in 24 hours. And so like, okay, but even if that was true, that's not enough for muscle growth. What you usually have to do if you want testosterone-driven growth, there's only about 3 published studies where they took the risk of actually giving normal people large amounts of testosterone for a long period of time. And what you see is, you don't need to just double it. You need to at least sextuple it. You need a 700% increase in testosterone, metered up through time, to get sustained muscle growth. You're shoving them through a second adolescence. And so therapeutic doses, if what you're trying to do is induce muscle growth, are up around 3,500 to 4,000, which is one of the reasons why the side effects proliferate, is you're giving super physiologic dose by a large amount. As you can guess, I'm not a big steroid fan. Another idea that you hear, has anyone ever heard, I'm sure, Greg, you've heard about IGF-1, people talking about IGF-1. And once again, I'm not denying that insulin-like growth factor is involved in growth. It truly is. This is showing you that when IGF-1 goes up, this will go up after insulin. There are actually people who will inject themselves with insulin before they go to the weight room, which I think is just massively stupid. Excuse me for saying it out loud, but it is. When insulin-like growth factor, and by the way, growth hormone and insulin both drive this up. It does stimulate satellite cell reproduction. So it's the A, B, IGF-1 stimulates satellite cell mitosis, and then one of these moves in. So you do add new mononuclei with IGF-1. Once again, that's critical when you're increasing the muscle size by 10-fold over your first 5 years or whatever. But this turns out in adults to be almost a non-pathway. It probably happens occasionally as a living mononucleus becomes senescent or becomes damaged. But it's amazing how little this works. And I will show you an example right now. These people, pygmies. You guys have heard of pygmies? These are either Mbute or Efe, I forget which book I took it from. Pygmies, they lived in the Ituri forest of what used to be called Congo. Their average stature is in the 4'6" range. If you look at their genetics, what they lack is insulin-like growth factor. That's why they're short. They lack insulin-like growth factor. Now, I admit that means that the insulin and growth hormone they have during childhood causes them to not elaborate as much person, right? They're smaller critters. You're appreciating that? But here's what I want to say. Do you see a deficit in their muscle formation? I admit they don't have optimal diets. That's either worms or a low-protein diet creates that funny little pot belly. But there's one of the guys way in the back. Oh, here. Yeah, very poor development of his pectorals, right? Absent deltoids. These guys have perfectly proportionate muscle. They're actually, if any of you would like to take on a 400-pound gorilla and kill it with a bow and arrow, you go give it a try. But these people are extraordinarily good at muscular activity. So that, again, is sort of an observational study that apparently in adulthood, as long as you're using, anyone here neutered their dog? Similar, this goes back to the steroids. If you neuter your dog, but you keep its physical activity, as soon as you neuter it, do they waste around to little skeletal beasts that look like anorexics? No, as long as you maintain their physical activity, the neutered animal is quite muscular. It's really good with pit bulls because they're naturally muscular in their growth phase. Then you deprive them of their testosterone. As long as you keep them active, they stay muscular. Once again, indicating that the things that drive growth in childhood are not the things that control our adult maintenance of tissue. So here is a study, a more interventional study done by Dr. Bodine and Espen Spannenberger when he first came here about 2005. And they were able to find on the market a mouse who has a mutation in their IGF-1 receptor, so that it is dysfunctional. It will not dock with IGF-1. So this would be called an IGF-1 knockout. I hope you're familiar with those ideas. Okay, good. So let's check this. Oh, let me bring in, do I have again, the knockout makes, do you have IGF-1? Let me go back somewhere. Oh, there it is. The knockout, oh, this is IGF-1 over here. The knockout has about 20% of the normal activity in terms of IGF-1 action. So you've knocked out a large fraction of it. And so if IGF-1 is critical for adult hypertrophy, this will block hypertrophy. We do the compensatory overload model where we cut the gastroc and soleus, overload the plantaris, and what you see is absolutely no difference between the knockout mice and the wild-type mice in the amount of tissue they add when you load their muscles. By the way, notice this, they appear to have, because they're younger critters and don't have as long a growth period, humans are big and have a long growth period. Notice that the knockout mice are smaller, just like pygmies are smaller, so their growth phase is a little less at the beginning. Yeah, I get that. But whatever it is that's causing muscles to enlarge in response to external demands seems to be intact, even if you block IGF-1. Am I making sense? So far it's sounding like nothing causes muscle hypertrophy. Just happens. Hang in there, be brave. So now I think we're ready for this figure. We're working on a presumption, presuming that in order to have muscle growth, we need to make more protein than we degrade, right? And since we all know that protein is coming ultimately from the DNA, we've gotten locked into what's sometimes called the central dogma of biology, which is first there's DNA, then you transcribe it into an mRNA, and then that transcript leaks out into the cytosol, where the ribosomes, what do we call that next step? Translation, turns it into protein, right? And so because of knowing that, and it is true, we've gotten kind of locked in. Oh, we need satellite cells. We need... Stay with me a moment. Because it turns out that if you are trying to do something fast, think about exercise uses hyper-responsive mechanisms to keep things under control. We tend to be very fast. Whatever is fastest is what will win if you're trying to make adaptation or exercise loading. So think about this. In muscle, there is a certain amount of tonic transcription going on, because didn't I tell you your thighs turn over like every 6 weeks to 2 months? There's always transcripts floating in the cytosol. So the actual fastest way to get an alteration in protein synthesis is, instead of reading this mRNA twice, read it 10 times. Did you track what I just said? That's called translation. The step is translation, and the term is translational efficiency. Simply read the same transcript many more times. That is not only the fastest way to get a change in protein synthesis. It also makes you less dependent upon mononuclear content. See how that is? You don't have to be doing expensive long-term steps like getting someone outside the cell to do a mitosis and then migrate through the cell wall and then establish itself. And wow, wow, wow. See how fast that would be? Just read the transcript form. So it turns out that in the process of translation, this will be a little review of you for you guys who forgot this. It is for me. Oops, I just turned off the. Maybe that's how the recording dies. Is I touch it with my thumb. Okay, carry on. Yes. So here's our mRNA that contains the information of the sequence for DNA. The initiation step turns out to be the rate-limiting step for making a protein. That initiation step is when a transfer RNA carrying methionine, the code on the mRNA is AUG, adenine uracil guanine. This is your initiate code. Start transcription, translation, start translation. And here's your transfer RNA that comes in and plugs onto this, carrying an amino acid methionine. And then that's the start of your protein. Okay? And this is what gets things going. So for those of you who've forgotten this, and I have, here's your mRNA. Here's your initiation codon, AUG. Remember, there's the transfer RNA. And the transfer RNA is a piece of RNA that will dock on a specific, here are the antisense codes, and carries an amino acid on the other end. Once it does that, if a functional ribosome, so there's a small piece of the ribosome which is 40, it's referred to as 40S in weight, and this larger component is called 60S. When you combine them together, for some reason, you don't call it 100, you call it 80S. That when the two are combined, they don't add up numerically, but this is the functional combination, and it's these two together that then will start to transfer and create polypeptide bonds. So here's your next codon. Here's the next transfer RNA with the antisense layout. It's carrying valine, and you've made a peptide bond. You're on your way. You're making protein. Is that, you guys have heard this before, right? I'm not talking crazy talk. And there is a termination code. I used to know a lot of these things. So do you remember the term polysome? So a ribosome and one mRNA with a single ribosome is, oh, look, here's a nice graph. That is a 20S subunit. 40S, sorry, 40S subunit. That is a 60S subunit all by itself. And this is a mass spectrometer reading of it. And so when they get together, which you young people say hook up, when these hook up on an mRNA, then you start to have a functional, and you can call that a monosome, but no one does. It's a single ribosome reading a transcript. Now, as I've just said, the absolute fastest way to augment your DNA synthesis is just get more ribosomes to line up and start reading. Can you tell that this was the first one on? It's got the longest poly. This one was over here first. You always start the 5' cap is where that AUG initiation sequence is. And notice it's got the longest peptide tail. Now these other ones are following along like ducks in a row, elaborating protein as they go. Right? So let me show you what exercise does, because this is leading us to what really causes muscle growth in adults. Here's a bout of resistance exercise with biopsy measurements of translation step, and we can actually count the increase in protein synthesis. You ready? In this model, it's fun. So at rest, we had the transcripts, which are always present. There's always, this is say it's a myosin transcript, right? You're going to replace a myosin somewhere. We have 1, 2, 3, 4, 5, 6 units of protein synthesis going on in this resting muscle. Got it? This is after one resistance workout bout. 1, 2, 3. 6 more is 9. 4 times 3 is 12 on to 9. 21. We've gone from 6 to 21. You've had a 300% increase in protein synthesis in a single workout. That sounds promising, doesn't it? Remember, this is real data. This is measured on, you can measure it on humans. I think it's done on animals. So, wow. That would work. Now, clearly, it doesn't go on forever. It's a short-term effect. But after each workout bout, you get an increase in translational efficiency. How is that happening? We've actually gotten somewhere. You realize I've just reviewed 30 years of research. Be brave. Especially when you see this figure, be brave, because it's easier than it looks. So it turns out, if you look down here, protein synthesis and muscle hypertrophy is controlled by things like insulin-like growth factor. It is affected by things like branched chain amino acids, right? These are very important after feeding. When you feed a child, you breastfeed a child, and it gets some branched chain amino acid, the child gets bigger over the next week. Yeah. Insulin is important for growth in childhood. I have to say that when you look at the effects of these, leading down to their pathway of this, the effect is maybe 1/10 to 1/20 of what a workout is. In an adult, exercise, especially resistance loading, is what drives this system. And so someone has included, that's why I gave you such a busy graph, is I wanted you to see that's a cell membrane, that's a those are phospholipid bilayer, yeah? What would these be? These proteins that span the phospholipid bilayer and hook into the collagen up there. Elastomers, yes? And again, most of us, this part is theoretical. There's people working on how does the muscle know how much force it's experiencing. But most of us think that somewhere involved in the costomer, there is like a functional moiety that flips out in accordance to loading. The harder you load it, the more this thing sticks out, and the more it can activate these intracellular phenomena. So, the intracellular phenomenon we're interested in is called mTOR. Has anyone ever heard of this? I know Greg said he did. So those of you interested in muscle, or in tumors, it's funny, in a lot of tumors, mTOR runs wild. What are cancers about? Uncontrolled growth. So in cancers, you lose the regular restrictions of growth, and thus you get these crazy giant cells that are constantly reproducing. But we're interested in the controlled growth of mTOR. mTOR stands for the mammalian target of rapamycin. Rapamycin is a peculiar, somewhat poisonous antibiotic, and you'll see why it is named this. I hate these names. mTOR should be called Adult Translational Initiator. That would be a good name. But this is the stuff, and what it is, it's a phosphorylated enzyme. You guys seem pretty comfortable with protein kinase, right? You get the idea that protein kinase, if epinephrine is high, or if there's high levels of energy use in a cell, protein kinase turns on, and it's a phosphorylase. And remember, a phosphorylase is is an enzyme that adds phosphates to other proteins. And so protein kinase will run around to all the protein. You have to take this, it's your phosphate. Here's your phosphate. I'm protein kinase. There you go. So protein kinase runs around to all the proteins for which it has specificity, hands them their phosphate. And surprisingly, most of these proteins that I've just activated are involved in replacing ATP. That make sense? Okay, so mTOR is a phosphorylated enzyme, and it runs around the cell activating enzymes. Guess what it tends to activate? Things that involved in the initiation of, so you start to get your ribosomes self-assembling. You recruit ribosomes from the nucleus. They move out into the cytosol. They self-assemble. So it increases translational efficiency is the primary thing it does. And this ultimately leads to enhanced protein synthesis, or polysome formation, and enhanced protein synthesis. Does that make sense? This is probably the mechanism of adult hypertrophy. I'm not saying the other ones don't have some role, but it's amazing how every time we try to measure it, it's not there. This is the one, I have to prove this to you yet. So the first thing would be, I think I showed you polysome formation goes up with resistance training. Let's look at mTOR with resistance training using the compensatory hypertrophy model. where we overload erects plantaris. And then what we're going to do is, it turns out this rapamycin antibiotic, the reason it kills things, is it blocks mTOR. If a cell can't synthesize protein as an adult, it doesn't do well. And so we would never use this on a human. But notice, in the control state, let's see, we'll look at the control data. Here's muscle weight. You do compensatory hypertrophy, percent change. Within 1 week, they've increased their muscle mass by 25%, and within 2 weeks, they're closing in on a 50% increase in muscle mass. Good grief. If you give them rapamycin so that their mTOR is turned off, remember how all the other studies I showed you, we blocked IGF-1, they still grew. We blocked satellite cell recruitment, they still grew. Well, here's one where we did it. We actually destroyed muscle hypertrophy, and these values are down around 5 to 15% of what ought to have happened. So, and this is the fiber cross-sectional area, again, showing you growth rates in the two different muscles. Again, it's about 10% of the muscle growth you'd expect if you block mTOR with rapamycin. So we found a culprit that fits the criteria of science. When mTOR is up, it seems to create polysome formation and synthesis, and if we block it, that synthesis stops. Is that okay? So in some ways, I hate to put you through that, but on the other hand, that's how science works. It really is. It's a lot like murder mysteries, where you have a list of suspects, and then you start eliminating them based on alibi and evidence, and finally you wind up with the committer of the act. Okay. So, this is good. Any questions? I was worried I had too much in here, but I think this is good. So, we're actually going to start to segue into tomorrow's lecture, which is going to be applications. And so let's take for now a working hypothesis that the main thing that grows bigger muscles in adults is mTOR activation. And while we get tiny activations from feeding behavior, like insulin and breast amino acids, the elephant in the living room of adult mTOR activation is resistance loading. That's what makes it happen. So let's pretend that and see if that's a useful model. Well, the first thing it helps you with, these are real humans with multiple biopsies. Let's focus on mTOR here. And you're noticing that this is after a baseline resistance training. So they lift weights heavily, this is their workout, and then you follow them over the next 24 hours. Notice that young people, these are young individuals, have a strong mTOR increase, and it persists for quite a long time. Older people, beyond age 60, have a much smaller mTOR increase, and if you look at the variability, after about 6 hours, they're not greatly different than rest. So they have a blunted mTOR response. Remember I mentioned the term old people start to have muscle wasting that we call sarcopenia? Well, this would be one thing. If your daily activity no longer maintains your muscle mass, well, that would be a problem. This term is often called anabolic. What you see in older adults is called anabolic resistance. That I can absolutely do the same workout as a fraction, right? I can't lift 100% of what Greg lifts, but if Greg is lifting 80% of his max, I could lift 80% of my max and do repetitions. What we would discover is old people, if one of you guys starts a weight program, you might have a 25 or 30% increase, gosh, just in 3 months. 3 months after I start my program, I've just started to add plates to the bar. It's sad but true. And it's probably based, the anabolic resistance of the elderly is probably based upon this blunted mTOR response. So this is starting to sound like it's a useful concept. Oh, I have it blown up so you could look at it. It's about a 20% blunting of the response. Another phenomenon that was first described when I was in grad school that we couldn't understand is it has been known all the way back in the 1980s that if you do very intense aerobic work combined with weightlifting at the same time, it has to be in the same period of time, the amount of hypertrophy you get is a lot less. Yes, sir?
You mean same time, like same day? Or
Same day, same hour, same muscle too. It's a really good question. Well, and this is the study that first brought it to our attention. It's Gittleson and Hickson did this together. What they had was groups, they were randomized. One group did 45 minutes of continuous endurance exercise, one group did 45 minutes of continuous strength training, and then one group mixed them. Did both workouts, so 45 minutes each, a 90-minute workout. Are you with me? This is the strength in 3 maximal lifts. I think it was squat, bench press, and curl. And what you'll see is, it's very interesting. So forget about the endurance group. There's no change. Endurance training does not change strength, and they knew that so well they didn't even bother to make measurements except at the beginning and the end. Okay? These are the 2 groups that are interesting. So notice that in the first month, even though the baselines are a little different because of who the subjects were randomized, notice that their rate of acquisition of strength is the same. Someone explain that for me based on what we've learned in the last 2 or 3 days. That's the neurological adaptation. And so and we didn't even know any of this stuff back then, but the data say what the data say. That's why you make good measurements, because sometimes you don't understand them, but your progeny do. So this is the neural phase. Where these guys really fall off the chart is when you enter the hypertrophic phase. Usually by the time you get here, most of these gains are coming from muscle growth, accumulating muscle growth. They appear to be damaged in some way. They're not doing it. And so this led to the idea that if you do endurance exercise, it has to be very high intensity. If you do it before a resistance exercise bout, that's okay. And I'll show you the details of this next lecture. I don't want to drive you crazy. But if you activate your mTOR and then immediately run an energy deficit inside that cell, it tends to turn the mTOR back off. Protein synthesis drops back down. You tracking that? So it has to be the same muscle. It has to be, Moses' objection is exactly right. It must be coincident. It has to be in the same hour. And what we think is happening, I'll explain this, I think maybe that'll be our last figure, is, let me first give you an analogy. So protein synthesis takes energy, right? It's energy expensive. You don't really see it catch up until the workout's done. You gotta rack the last weight and then go rest. And you start to see a real spiking of protein synthesis. Make sense? What if you rack the last weight, you take that muscle, and you suddenly start to drive its adenylate charge down with repeated high-intensity runs? This is somewhat like remodeling. You're remodeling the bathroom, and then suddenly the house catches on fire. Most reasonable people would stop remodeling the bathroom and leave the home until the fire was out. Does that make sense? That you're in an energy emergency, and so there's an evolved shutdown mechanism to turn off. Why are you doing that energy expensive thing when the house is on fire? Leave the building until it makes sense. So we'll develop that idea more next time. But this phenomenon was completely unexplainable when I was a grad student, and now watch. We have learned, so here is, you might want to put a line through this, and that's why they're different colors. This is the response to endurance training. This is the response to heavy loading. And Morgan, I bragged on you, I don't know if you listened to the podcast, I was bragging about how you pointed out both of these lead to protein synthesis. It's just different proteins, mitochondrial versus sarcomeric. Well, there is a one-directional crosstalk. Weightlifting does not turn off mitogenesis. But this talk, if you have a very huge energy deficit stimulated, at the time, right after an mTOR spike, resistance training, notice that these are phosphorylative inhibitions of both upstream and downstream areas that lead. So this is the energy deficit says the house is on fire, stop all that expensive synthesis activity. Cool. So the mTOR model, not exactly, I can't believe I showed you 30 slides, but this leads us to exactly what we want to do. This is probably if I was going to say, this is a good modern way of looking at how muscles grow. And so you know what is going to be fun about next time, tomorrow, if I succeed in building your lecture.